So far in Chapter 12 we've looked at parabolas, and we looked at circles, and then we looked at ellipses. All three of those are considered part of a group of figures that we call conic sections. We're going to look at a fourth one today, and that's a hyperbola. We've actually looked at hyperbolas prior to today when we looked at them back in Chapter 2 when we were looking at inverse variation. Just like we did with the other figures, we want to define it geometrically, and then we're going to define it algebraically as well. So let's first look at it geometrically. Okay, so the definition of a hyperbola is very similar to the definition of an ellipse, with the major difference being our focal constant. Instead of it being the sum of the distances between the focus points and the point, it's the difference of those distances. So here's the actual definition. Let f1 and f2 be any 2 points and d be a constant, with d being a value between f1 and f2. Then the hyperbola with foci f1 and f2 and a focal constant of d is the set of points P in a plane that satisfy pf1, or the distance from P to f1, minus the distance from P to f2 is equal to that focal constant. Notice we have absolute values around that. The reason for that is we're talking about a distance, so it's always got to be a constant value. Okay. Some parts of a hyperbola: it has vertices. The vertices are v1 and v2 on the drawing here. It's where the hyperbola will intersect the x-axis. Okay. And that axis would be the axis that has the foci points f1 and f2. The asymptotes of the hyperbola are L1 and L2, these lines here. And remember that the asymptotes are the lines that a hyperbola approaches but never touches. So the hyperbola will continue to get closer and closer and closer to those lines, but it will never touch those lines. Okay? So geometrically, that's what it is, and it's kind of like, if you think about an ellipse, our focus points kind of were inside of the ellipse. As soon as they kind of move outside the ellipse, that the ellipse turns around and kind of splits in half and becomes a hyperbola. Now that's not an actual mathematical definition, that's just kind of a way of kind of thinking about what's happening there. Okay, so now let's look at the hyperbola from an algebraic standpoint, and we're going to start by looking at the standard position of a hyperbola. And what we will have, and that's all we're really going to look at right now, is a hyperbola in its standard position. And that's going to be a hyperbola that's centered at the origin with its foci of on one of the axes, either the x-axis or the y-axis. Okay? So the equation for a hyperbola, the hyperbola with foci of c0 and negative c0, and a focal constant of 2a. So that focal constant, that distance that we talked about up here, okay, this distance, okay, is that focal constant. So our focal constant will always be 2a if it's on the x-axis, 2b if it's on the y-axis. Okay? So here is that equation then. It would be x squared over a squared minus y squared over b squared is equal to 1. And we're going under this with also knowing that b squared will be equal to c squared minus a squared. Okay? The standard form for an equation of a hyperbola then is also in that exact same form: x squared over a squared minus y squared over b squared is equal to 1. Notice how the form is exactly the same as the ellipse, except for, just like that focal constant, we were taking the difference with the hyperbola and the sum for ellipse. Here, when we have our standard equation, it's the difference between the x squared over a squared and y squared over b squared. Okay? At this time, if you could just take a minute to stop the video and read through example 1 on page 833. Okay, let's take a look at number 1 here. It says find an equation for a hyperbola with foci of f1 and f2, where f1, f2, in other words, the distance from f1 to f2 is 26, and the difference between their distances to that point is 10, on a rectangular system in standard position. Well, But if it's on the x-axis, we got to think about the information that we're given and how we can get information for our equation. So there's three things that we're looking for. What is A, what is B, and what is C? Okay. Well, remember that A and B are the values that are going to give me what I'm going to have underneath here. So that's going to give me these values. And C is the foci point. And sometimes I need C to figure out what B is. Okay. Well, the F1, F2, those are the focus points. Well, I know that my focus points are at C0 and negative C0, if it's on the x-axis, that is. Obviously, that would be 0C and 0 negative C if it's on the y-axis. So if the distance between those two is 26, and we're in standard position, that means the center is at 0, 0. That means I have to go 13 units to the left on the x-axis and 13 units to the right. So that means that my two focus points are at 13, 0 and negative 13, 0. Okay? And my C value is 13. Now, the second piece of information is that would be my focal constant. So that's that value for the focal constant, and the focal constant we know is equal to 2a if it's on the x-axis. So that means that 2a is equal to 10, therefore a is equal to 5. So we've gotten two of the three things that I need to know to find my equation. To find the third, I'm going to use this b squared equals c squared minus a squared. So I can say b squared is equal to c squared minus a squared. And if I do that, go to my calculator to get that value. So b squared is equal to 169 minus 25, or 144. Therefore, b is equal to 12. So now I know what my a is and I know what my b is, so I'm going to write my equation. So it's going to be x squared over a squared, which is 25, minus y squared over b squared, which is 144, is equal to 1. From an equation standpoint, the asymptotes can be found fairly easily. All you need to know is what a and b are. So the asymptotes, or those lines that the hyperbola approaches but never touches, would be plus or minus b over a times x. So y equals plus or minus b over a times x. Okay, that would be the line that the hyperbola would be approaching. Okay. So the last section then is graphing a hyperbola with an equation in standard form. So if we have it in standard form, we want to be able to graph it. So at this point, if you could just take a minute or two, stop your video and read example number 2 on page 834 before I go over this example number 2 here in your notes. Look at recording graphing this hyperbola. It says graph the hyperbola with the equation x squared over 25 minus y squared over 4 equals 1. Include and label vertices, foci, asymptotes for the hyperbola. Well, I'm going to start with the asymptotes. The asymptotes gives me kind of a good shape of what that graph's going to look like. So I know my asymptotes are y equals plus or minus b over a times x. So in this case, y is going to be equal to plus or minus b over a. B would be 2, so that'd be 2 over 5 times x. So we have y equals 2/5 x and y equals negative 2/5 x. So if I come down here and use slope-intercept form, so the intercept is at 0, 0, slope of 2/5, so up 2 over 5, or the slope of negative 2/5 up 2 over negative 5. So these would represent those two asymptotes for my hyperbola. The next thing I'm going to do is I'm going to get my vertices. Well, my vertices, remember, are at a0 and negative a0. Therefore, my vertices are going to be at 5, 0, and negative 5, 0. So I'm going to plot those values on here. So that's where my hyperbola is going to intersect the x-axis. Okay. And then, so we've taken care of the vertices, we've taken care of the asymptotes. We need to find the foci. Well, to do that, I know what my a squared and my b squared is, but I need to find my c squared. And to do that, I'm going to use this right here. This b squared is equal to c squared minus a squared. Okay? So I can say b squared, which is equal to 4, is equal to c squared, which we don't know, minus b squared, or minus a squared, excuse me, which is 25. So if I add 25 to both sides, I get c squared is equal to 29. Therefore, c is equal to the square root of 29. Okay, which means that my two foci are at c 0 and negative c 0, so that would be at the square root of 29, so somewhere right about in this range, and I'm going to label that as the square root, negative square root of 29, 0, and same thing over here, whoops, the square root of 29, 0. And so we've labeled the foci points, we've labeled the vertices, we've labeled the asymptotes. Now it's just putting in the shape of our hyperbola. We know that it's going to continue to get closer and closer to those asymptotes. We know kind of what that general shape looks like in terms, and also where the x-intercepts are. So this is kind of our general shape of what that graph should look like. And that's all we're really looking for there. And then we want to also label these, so this would be y equals negative 2/5 x, and this is y equals 2/5 x. Okay, and our vertices we'll put as negative 5, 0, and 5, 0. And I think we have everything labeled.